Great, so let's get started. So welcome back, everyone. We are talking about clustering. This is going to be the third and the last lecture on clustering in this course. The main thing we'll talk about is going to be the mixture of Gaussian's formulation. So this is kind of a very similar but more kind of statistically modeling based version of the k-means thing that we talked about on Tuesday. I probably imagine when I first write it down, it will look fairly complicated, and then we'll see what is the most common algorithm for this, and you'll see, okay, it's not actually that much more complicated than what we did to solve the k-means problem. So we'll plan to talk about a couple of other things as well, including things like soft clustering, which is kind of a different way of thinking about clustering that fits into the right way to do mixture of Gaussians. And then if we have time, I'll kind of give you a foray into kind of the vast universe of clustering, and we might talk about a different clustering algorithm. The one I had in mind was the mean shift algorithm, which is mean shift clustering, which is kind of a just completely different way of approaching this whole kind of problem of what are we supposed to do for clustering. Great. So just quickly look at the schedule. The last lecture for clustering today will move next week onto classification. We'll have 4 lectures on classification, no class on Thanksgiving, and then we'll have the last lecture of the semester. We'll plan to do that on a review. We'll get to kind of go over. I'll probably go over some of the things that I think the class had a little bit more trouble with, and then there's actually linked off here. Oh yeah, there's a practice exam linked off down here at the bottom. This is not kind of what the exam, the very bottom right of the screen if you're on Zoom, and it's not like that one is much longer than what your exam will be. It's more comprehensive. Think of it as kind of a superset of the topics you will see on the final exam, but it will give you a taste of it, right? If you can answer that practice exam, all the questions, you probably have a pretty good kind of grasp of everything you learned in the class. So if you're starting to think about that. Okay, homework 5, the last homework, it's probably ready. I just want to go over it a bit more, and I'll probably post it by the end of the week. That's not due until December 10th. Okay, so that's a while still. And then there's one more quiz. It won't be on Thanksgiving. It'll be the next Thursday. That'll be the last quiz, and it will cover including clustering and the first 2 lectures of classification. All right, so that's kind of the rest of the schedule. We're getting close to the end here. Great. Let's get to the lecture. All right, so we're talking about this mixture of Gaussians problem, and kind of again, our goal here of this section is of the course is clustering, right? And if you remember, the goal of kind of the way we had talked about as clustering was the input here was going to be a set X. Let's say this is in RD. We'll assume that these are going to be in RD. We're going to be given, we'll be given some way of measuring how similar 2 things are, but we'll also be given a value K. Okay, and I'm not going to write the distance. We're going to kind of use a model That's going to kind of change how we think about the distance a little bit with the mixture of Gaussians. But I want to first kind of make one other change to your thinking. And then the goal is going to be a decomposition of X into disjoint kind of sets S1, or let's see, we call these X1, X2 up to Xk, where each Xj is going to be a subset of X, and Xi intersect Xj is going to be equal to the empty set, right? So there's the disjoint kind of decomposition. Going to have data. Think of these data in these three sets. This is our sets X, and we're somehow going to decompose this. And we talked about this Voronoi diagram kind of from centers gave us some way of decomposing it, but really there are these three sets here, X1, X2, and X3. And these are kind of disjoint kind of decomposition. Each of these would be a cluster, right? So these are the clusters that we're after. Okay. Okay. We are going to, and there are different ways of saying what's the best way of doing this decomposition, right? We talked about the assignment-based clustering with k-mean, where you pick centers and then you minimize the sum of the squared distances onto the smallest center. What I want to talk about of kind of a change of this is called soft clustering. Okay, soft clustering is going to be so different, and the soft goal is not going to be a disjoint sets. Okay, I'm instead going to kind of assign every data point onto a kind of a subset of sets, but with weights associated with them. Okay, with the soft goal is an a assignment of each X in X, so of each of the data points to each so set, or let's say each cluster with with some probability. All right, so I'm going to have something like the probability that, and there are different ways of thinking about it. Could be a weight instead of a probability, but you can think of the probability that X is going to be in, let's say, Xj is going to be equal to something like the probability of, let's say, P of J of X, right? So I'm going to assign everything with some probability. And so this means I can assign it to multiple sets. Now the probability, right? Each of the probabilities needs to be between 0 and 1, right? So if it was exactly 0 or 1, right? It's with probability 1, like in the hard clustering formulation, the original one, each of the points was assigned with probability 1 into its cluster and probably 0 into all the other clusters. Now we're going to say, well, I don't know for sure. I'm going to kind of like hedge my bets a little bit, right? I'm going to say, well, it's probably in, if I picked one of these points here, let's say this one, it's probably in X2, but maybe it's in X3, right? Maybe this one I've circled up in the right is actually in X3, right? This is more interesting, for instance, when I get a new point right here, right? This point, and there are kind of these distinct sort of kind of shapes which define these clusters. And this one is not really in either of them, in any of them. And it's kind of in the boundary between all of them, right? That one I might not know exactly which cluster to put in. Now I can put this in X3 and say that's the one, that's the Voronoi cell it belongs to. So I'm putting it in X3, but maybe I'm not so sure. So I'm going to give it a soft assignment. So typically when you do this, most of the values are close to 0 and 1, but some of them are on the boundary. Some that are a bit murkier, and I don't want to kind of make a really hard choice here. Okay, that's the kind of way of thinking about it. So let me try and, okay, so, and then in order to define this sort of formulation, we want to optimize some function for this again, right? We want to come up with, say, what's the right way of doing, kind of what do I want out of the clustering? And then I need to kind of optimize that. You know, if this one was a little bit messy, the hard clustering formulation, the soft goal is going to be a little even more messy in how it's formulated. But as we'll see, kind of, you know, they're kind of, it's, you know, it's building on what we've already done, and it's not going to be too bad. All right, well, let me do another example here just to help you think about this a bit more. Okay, actually, let me do a much smaller example. Okay. Let's see here. Okay, so I'm going to kind of go back to this assignment-based idea, and we'll call this C1, this C2, and C3 here. And you can kind of think of some like Voronoi lines here. Okay. Just based on these, but I don't want to make my assignment entirely based on them, right? So I would probably say that these points, I might say, right, just for a simple way of thinking about it, these 3 points, let's call them X1, X2, and X3, that the probability of, say, X1 is in cluster X3 might be equals to 1. I might still say that. These are definitely in cluster 3 as I've defined it. This point X4, well, that one is less clear. And this point X5, well, this one, it's kind of in C2, but it's kind of leaning towards, it's in cluster 2, but it's kind of leaning towards so cluster 3. Okay, so one way of thinking about this, and this gets into kind of as computer scientists, you might be thinking about how would I implement this? And one way of doing it is, and something I would kind of recommend if you're going to implement something like this, is to think of having the point IDs, right? They're up from 1 through 10. This is X6, X7, X8, X9, and X10, right? And I would think of just storing an array, and then I'm having an assignment onto the cluster, and I can store this as in the hard clustering formulation. In the hard formulation, I would store this, okay, 8 to 9 and 10 are in cluster 1. 1, 2, and 3 are in cluster 3. So I just give the index of the cluster it's supposed to be in. X4 is also in cluster 3, and 5 and 6 are in cluster 2. There's kind of a hard assignment here, and I just store the index of the cluster. That's how I might represent this if I'm writing code. Yeah.
So when you have your centers, usually do like points out to get that, or you just kind of like arbitrarily choose like
Yeah, so I haven't talked about the algorithms yet. I'm just trying to explain the models, and with the soft clustering, we will see an algorithm that's a lot like Lloyd's algorithm. It's kind of a generalization of Lloyd's algorithm. You can think of it like that, and it will deal with the soft assignment. For now, let's just say I have these clusters, and I'm trying to think about what it means to have a soft clustering and how I would represent it. And I think this will help kind of make things more concrete when we actually talk about the algorithm, right? But it'll be like Lloyd's, but then we're going to need to switch it up a little bit because, well, with Lloyd's algorithm, I took like an average of a set of points. Well, now if a point is not entirely in a cluster, how do I account for it in the average, right? And there's multiple ways you can do it, and I'll tell you what is generally kind of considered the right way of doing it. Okay. Okay. On the other hand, if I do a soft formulation here, right? So in the hard formulation, I just store the index of the point. But in the soft formulation, I would probably store actually kind of an array. And I'm going to then, let me shift these over a bit. Okay, I'm going to kind of store an array for each of the clusters, and I'm going to assign like probabilities here, right? So 1.1, which is kind of is this guy, which is in cluster 3, right? He is that point is not going to be in cluster 1, not in cluster 2, and with probability 1 is in cluster 3, right? And I'd probably do similar here, okay, for all of these guys. And for, let's see, X6 and X7, right? X6 and X7 are probably pretty clearly in cluster 2. So let's go and mark those. That'd be 0, 1, 0, 0, 1, 0, right? These are probability distributions here, but they're pretty simple ones. And then let's say 8, 9, and 10 are all in cluster 1. Okay, but then, right, that's the guys. But what is left are these 2 points, X4 and X5, and these are going to be more interesting. So then I would store something else in here. X4, let's say the probability it's in cluster 3 is the highest. That might be 0.4. And the probability it's in cluster 2 and 3 might be 0.3 and 0.3, right? This is now this kind of little column here. This is a probability distribution, right? So these should all add up to 1. They should all be between 0 and 1, right? And so it's slightly more likely to be in cluster 3, but it could easily be in cluster 1 or 2. And then X5, I might do something similar here. Right, so for X5, I might say, well, it's probably in cluster 2, let's say 0.8, but it might be in cluster 3, so 0.2 and 0 up here. Right, so for X5, it's going to get this different probability distribution. Okay, so think of this as how you would store it, and this is kind of what the soft clustering is representing. Okay. Okay, now these are again quantities that will be useful to use, and will eventually, I think what I will describe this as, let's see, what will notation I want to use is, yeah, okay, so I'm going to say that the weight that a point X, let's say X4 is in cluster 3, this weight is equal to the probability that X4 is in the cluster X3, and this is equal to 0.4. Weight 3 of X4 is in the weight that it's the probability it's in cluster 2 is 0.3, and the weight that's in cluster 1 is also 0.3, right? So I'm going to give these a weight. So I'm going to have a weight. These weights will end up being probabilities, and that corresponds with this column here. Okay. So I'll later in the lecture use these weights, and we'll see how we are going to get those weights. But I'm going to think of instead just of storing the assignment. just storing this probabilistic assignment. Okay. All right, okay, good. So this idea of soft clustering, how would I do a soft clustering? How would I actually calculate these? There are many ways of doing it. One kind of interesting way I'll throw out there that has to do with like the Voronoi diagrams. It's called like natural neighbor interpolation. Basically what I would do is I would say, well, I have, again, centers C1, C2, and C3. Let's say I decide to put a new center at C4 in order to determine its weight. Okay, I put a new center there, and what I would do is I would, let me change colors a bit. Let's say I put a new center here. It's going to change the Voronoi diagram here, and I'm going to kind of get new Voronoi edges, right? Some of them are going to be the same as before. The ones on the shared boundary between C3 and C1, that's the same edge before, but there are new edges here. And then to determine the weight of this point inside of here, and for each of the Voronoi cells, you know, I look at the area of its Voronoi cell that intersected with the old Voronoi cell of C3, and I take the percentage of this yellow region compared to the whole area, and that's the probability, right? So this is called so natural so neighbor interpolation kind of weight, and this is just one way of assigning these weights. Okay, this one has some nice smooth properties, but it's a bit kind of harder to compute than some of the other ones. But we'll talk about another way based on kind of some some probability distribution modeling. Okay, so this is just kind of going back to Voronoi diagrams and give you one example of what could be done here. Okay, so let's talk about, now let's get into this mixture of, so Gaussians, okay? And so this is going to be a soft clustering formulation, okay? My input is going to be X was going to be a subset of RD, and a parameter K, right, which would mean the number of clusters, soft clusters I'm going to have, and my goal is going to be a set of K, so Gaussians, and I'll review. A Gaussian is a d-dimensional or a distribution with a d-dimensional domain, and I'll review what that is. There'll be a probability distribution. So set of K probability distributions that is going to maximize the product. So I'm going to say the product of X times some, so times the sum over J equals 1 up to K times the weight that X, the point X is assigned to the Jth cluster, soft cluster, times the kind of the associated, so PDF of this cluster. It's going to have two parameters, mu and sigma, which we'll explain, and X. Okay, so this is the, or yeah, this is, well, this is the so the likelihood of X given, and these are, that's mu J, and so sigma J likelihood that given, yeah, the likelihood of X given, so Gaussian described by mu J sigma J. Okay, so again, it's going to be the kind of the overall, the joint likelihood, right? So it's a joint likelihood, okay, of all the data set, right? So I'm going to, again, this is predicated on the joint likelihood of these X being somehow being independent in some way. If each of the data points in X, remember X equals X1 up to Xn, right? These data points, let's assume they're kind of independently generated from some underlying distribution. Okay, so I want to have the joint likelihood of all of them. So I take the product of each of the individual ones because they're independent. Okay, and then this is corresponding with the individual likelihood of a single point, the sum over the different clusters. Say, well, it might be this cluster or this other cluster, right? I don't know which one, so I'll kind of use a weighted average of them, and then that's just the likelihood it came from that cluster. Okay, this seems kind of complicated, should bring back some memories from early in the semester. And yeah, and let me write up the PDF associated with a Gaussian. Okay, and this is not going to make it look less complicated, but it's basically 2 pi to the power d over 2 times the 1 over the square root of the determinant of the covariance matrix. So this uppercase sigma is going to be a d by d matrix. Mu, yeah, so mu is going to be a mean, that's basically an RD, and sigma is going to be a d by d matrix. This is going to be the covariance matrix. We'll explain this a little bit. In a bit, it turns out it won't be that hard. And then remember, to the e to the negative 1/2 times x minus mu transpose sigma inverse x minus mu. Okay. All right. So this is a d-dimensional, so Gaussian PDF. Okay. So if I evaluate this point x, this is how I evaluate it. Okay. So let's look at this just a bit here. This looks kind of like what is going on. The first 2 terms here are just normalizing factors so that when I integrate this, it integrates to 1. Okay, don't worry about them. I want this to be a probability distribution, so it integrates to 1. Actually, in the algorithm, we won't even need to compute these. Okay, we won't even need to compute them. I'm just writing them up here so that I get a probability distribution. The determinant, maybe you've seen the determinant of a matrix before. I basically define it in the book, in the notes someplace. It's some scale factor. Okay, it's you know, it's some scale factor. Okay, so the first 2 terms here, right, which are these guys, these are just scale factors. Okay, so this is just so it integrates to 1. Don't worry about them. Okay. The second term is e to the negative some quantity here. Okay, let's yeah, maybe I can write this up here. Let's look at minus 1/2. Remember the normal distribution, e to the minus kind of the x minus the mean squared, right? Yeah, so a normal, right, which is a 1D so Gaussian, right? This was basically x to the minus kind of x minus mu squared divided by, say, 2 sigma squared. Right? This was a normal distribution without the coefficient in front, right? It's the distance from the mean divided by this standard deviation, everything squared. There's a factor 2 in there that's typically written up. We still have the negative and the factor 1/2. Those are the same things. The sigma, this is an uppercase sigma, that's a lowercase sigma. Those correspond with basically this same thing here. This is kind of a squared built into that. It's usually not written in the uppercase sigma. Okay, so if I look at this sigma squared, that's going to correspond with this sigma term right here. Okay, and if I look at x minus mu transpose x minus mu, so I've taken out that, I've ignored that sigma squared. Now I can't completely ignore it, but if I do ignore it, well, this is equal to x minus mu norm squared, right? This is that's a dot product. A dot product of something with itself is a squared norm. Okay, so that's basically just the distance to the mean squared, which is kind of what we had with the normal distribution. Yeah.
Should that be the factor, the sigma?
No, this is sigma to the inverse. I actually want a full matrix here. Yeah, so I'm going to do I'm actually doing this is a d by d matrix. It's the inverse, and I'm doing a vector times a matrix times a vector. The x minus mu transpose is going to be a 1 by d matrix, right? So this is 1 by d, this is d by d, and this is d by 1, right? So I can do this matrix, this matrix product here. Okay, it's going to give me back a scalar though, right? So it's going to be like a dot product. I'm just inserting this d by d matrix in the middle here. And this is a little bit weird if you haven't seen this before, but it's kind of like a stretched dot product. Okay. Okay, so this is, yeah, let's go on the next slide here. Let's look at now at, I'm going to call this distance m. Yeah, so distance m between x and mu is going to be x minus mu transpose m x minus mu. This is called the Mahalanobis, so distance. And this is kind of a nice, it's a metric as long as m is going to be so positive definite, right? So this is the distance, and we're basically, or this is, it's actually, yeah, so it's actually the square root of this, okay? And because we're gonna have basically a squared distance, so the d sigma inverse of x mu squared, right, is exactly this mu trans, right, is exactly this term, the squared distance. And that's what we're putting inside of the exponent. Okay? And this is a matrix inverse here, because I'm kind of like dividing. Remember, with the normal distribution, I divided by sigma squared, right? So I'm putting the inverse of the uppercase sigma squared here, because that's kind of like dividing. Okay? If sigma squared is the, so if sigma is the identity matrix, then d sigma inverse of x mu is equal to, is just the Euclidean distance. Okay, I recover the Euclidean distance. That the inverse of the identity matrix is again the identity matrix, and if I multiply a vector by the identity matrix, it doesn't do anything, right? So if I have the identity matrix here, I'm basically not, I recover the Euclidean distance. If I have, let's say instead, if sigma equals sigma squared, lowercase sigma squared, so it's still a diagonal matrix, right? So if it looks like this, then this inverse of x mu, right, is going to be equal to x minus mu squared, or squared, divided by, so sigma squared. I'm basically dividing every coefficient, right, by sigma squared. This is applied uniformly in all of the terms, so I can just bring this down below. So this is basically kind of the normal thing we think about as a multidimensional, so multidimensional Gaussian. This corresponds with the case where I'm just kind of shrinking the distance. I'm saying what is kind of the distance here. If you remember, a Gaussian or normal distribution looks, it's not a great drawing, looks kind of like this, where this is the mean, this is one standard deviation, and it kind of drops off. In fact, it drops exponentially, goes exponentially down to 0 after about 1 standard deviation. And so this kind of says what is close and what is not close. Okay, these things are close, these things are far away, and so this sets the scale, right? So if I just have a diagonal matrix of sigma, then this is saying the scale of what's close and what's not close here. If I just have 1, then I'm saying, well, the scale is just whatever, a distance 1 is that scale. That's kind of implicit. If I'm doing, now, if I have sigma equals sigma 1 squared, sigma 2 squared, up to sigma d squared, so still a diagonal, then what I can think about here is this multidimensional. Let's say for d equals to 2, then what I'm going to do is I'm going to shrink more. I'm going to basically I'm going to have this. I'm going to think of having a sigma 1 in this direction and a sigma 2 in this direction. And this will kind of give me this like ellipse of these things are close. If I'm inside here, again, this point here in the middle is mu, and inside here is close, and it kind of starts dropping exponentially off as I get outside there. Okay, and so that tells me, well, the first coordinate is scaled by sigma 1, the second coordinate is scaled by sigma 2, and this is in the original coordinate space. Okay? What happens in the general case where I have sigma equals, everything is not a diagonal matrix here? What's going to happen? It's going to be, okay, it's not going to be a uniform scaling, right? It's going to be a scaling that's going to be kind of non-uniform. Certain directions are going to be scaled more, right? What I'm going to do in that case is I'm still going to have mu in the center, and there's going to be some V2, and there's going to be some sort of ellipse that's going to describe the scaling, but it's not necessarily going to be aligned with the axes, right? And I can find this by doing the eigen decomposition. The basis of that that ellipse are actually going to be the eigenvectors, and the scaling is going to correspond with the eigenvalues. Okay, so kind of I can picture this as I'm saying there's some distribution of data that I'd like to Yeah, so I'm talking about what is close and what is far. Okay, and so now our goal of fitting is I'm going to have some data which is just one cluster. Okay, this is just one cluster, and what I'd like to do is to identify mu, which is the center of that cluster, identify V1 and V2 and some corresponding scaling, and kind of say, well, this clustering is this is the data points that are close inside the cluster, and as I go outside of it, I might not be so close inside the cluster. This is going to be kind of our representation of one kind of cluster, right? It's going to be described by kind of mu, which is the center, and so sigma, which is the kind of the covariance. It's not just the variance, which would be kind of lowercase sigma squared, but the covariance, which captures that it can be changing, dropping off differently in different directions. And those directions don't have to be aligned with the axes. And kind of we can use our thinking about what the kind of the singular value decomposition or eigen decomposition was doing in order to kind of think about how those are represented. Okay. X mu in the norm. Oh, I'm late on this question. X, this here, X minus mu. Yeah, that was it. Okay, great. Okay, so this is how we want to represent a cluster now. And it turns out the right way to do this is actually through soft clustering to get kind of this. If you go all the way back to this probabilistic way of modeling this, you actually want to do this as a soft clustering, not a hard assignment. Okay. Okay, so this is the basic idea of what we'd like to do. We'd like to fit a Gaussian, a multidimensional Gaussian to each cluster, and we identify K of them among the data. And in fact, kind of the sort of scenario where this would be really interesting is I have one kind of distribution coming from here, another one coming might look like this, and then maybe another one down here. And I'm going to get kind of three kind of clusters. This is going to be mu1, sigma 1. This one here, this will be mu2, sigma 2. Right, this is mu1, and then a third one down here, mu3, right? And this is, right, so, and they could be different shapes, right? The shapes don't need to be the same. I fit the shapes independently. They could be different kind of the densities could be very different. This one could be much denser than the other ones. And I'd like to find this. And if I do regular sort of k-means clustering, it's not going to be, maybe it works in this case, right? But it's going to be hard to kind of fit this part of the data where the red and the blue cluster are close to kind of overlapping each other. Yeah. Yeah, and the clusters can cross over each other. Yeah. Yeah, it could be they cross over, and that's where actually, I mean, these do cross over a little bit, right? It doesn't end here. It's a probability distribution with infinite support. So it's, and so kind of understanding what to do when I have a point that's right here, how do I assign it to those two clusters? Well, that if I don't use the soft version of clustering, then it gets snapped to 1, and then when I try and estimate these probability distributions, it does not give the right estimate. So I do actually need to worry about them crossing. Yeah. Is that okay? Yeah. Right. So this can handle kind of these sort of things, right? And this is the sort of model we'd like to do. Okay. So okay. So let me see what I got myself into here. think, okay, so I think described, like, okay, I've described the model pretty well. Do people have questions about this model, right? This formulation is a bit kind of, it seems very much more complicated than what we dealt with before. And then I'm going to move to the algorithm, and the algorithm might make it seem even simpler, because the algorithm will look a lot like Lloyd's algorithm, okay? Except we just need to, basically we need to add 2 steps that are inside Lloyd's algorithm. One to deal with the soft clustering, which will be, I think, should be fairly intuitive, and one to deal with estimating, like the mu's are basically the same as the centers in Lloyd's algorithm, but we need to estimate also the covariances. And it turns out the covariances are kind of, there's a straightforward optimal way of doing that, and so that's also going to be pretty easy. Okay? Yep.
Just to clarify real quick, clustering, jumping back. Same way in regression is trying to show some correlation between the separate variables and what the outcome will likely be. Clustering is kind of doing the same thing, but restricting it to only certain ranges. Essentially, it's showing that within those ranges, the outcome is likely as predicted. It's just kind of another help to assume what outcomes will likely be, or rather.
Yeah. Right. Well, okay. So again, regression was the biggest difference, first of all, is regression was supervised. So we had labels. We're trying to predict these labels. And if the labels are scalar values, then we're predicting, that's used to predict the scalar values. That encompasses all of regression. Clustering is unsupervised, so we're just really trying to understand kind of the shape of the data. We don't have labels to guide us. We're not necessarily doing like prediction. What we might want to do might be something like, you might be able to say, well, I don't want to get rid of that guy, but if I do have this, new point, and I did fit these models, and I said, well, I looked at them, and there was like a talk I saw, so yesterday that I was looking at some crime statistics in by Purdue University, and said, well, there were 2 kind of clusters near each other. One of them had more that was on campus, so there was more public intoxication, and one that was in downtown, and that one was more theft, right? And you could see that, okay, there are these 2 different models that I found by clustering, and then I wanted to I have a new data point, and I want to say, okay, it's a crime. What do I suspect the crime to be like? Or if there was like a patrol in this area, what would I expect there? And so I'd like to make a prediction. If it's inside of these, I can make a good prediction. The likelihood is high, but it has likelihood associated with each of these clusters, it's just smaller. I have less information. So that might be kind of like prediction here. Should mention crime prediction, predictive policing. There's a number of fraught issues with that. So in case you're wondering about that, but I'm not going to get into those today. All right. Okay. One more question in the chat. Okay. Can you reiterate what each sigma parameter looks like? Yeah, kind of. Okay, yeah, so let me try and go through this here. Let's look at this first cluster, and I'm going to assign it 2 vectors, v1 and v2. And so what we're going to have is sigma 1 is going to be a matrix. D cross D, okay, but sigma 1, I can think of this as actually the SVD of sigma 1 is US V transpose. Okay, thinking about sigma 1 by itself is going to be really hard. It's going to be D squared different numbers. But if I think about by its SVD, and in particular, I can think about, well, V transpose is going to be equal to V1, V2. These vectors, and these V1 and V2 correspond with these two directions of this vector here. And then S is going to be diagonal, right? Sigma 1 and sigma 2 and 0 and 0. This one has to be diagonal because I took the SVD. And then this corresponds with the scaling corresponding here. So actually, yeah, so these correspond with the lengths where the length of sigma, of sigma 1 means I'm going to go further out here, and whereas sigma 2, the length is not going to go as far. V1 and V2 were, so unit directions, they just gave the direction of that ellipse, and sigma 1, sigma 2 gave the scaling. Again, U here is not so important. In fact, yeah, I don't actually need the SVD. I can actually do the eigen decomposition. So it's actually V, I can think of it as S, V transpose, and then this is actually going to be sigma squared. These are going to be squared terms here, because that's actually the eigen decomp. Okay, of this where sigma 1 equals to x1 x1 transpose x1, right? So this is all the data that was lying inside of that cluster. Then this is going to be sigma 1, x1 transpose. Okay. Okay, yeah. So hopefully that helps you understand how to think about this. Yeah. So that's why we did this after we did the dimensional reduction. Again, we don't need to do dimensional reduction here. We're just going to compute this matrix sigma 1, and we'll see we don't need to do the SVD, but to think about what the structure means, I think the SVD is very helpful here. Okay, let's talk about the algorithm. And this will basically, this I think is called, this will basically be the EM, so algorithm for mixture of, so Gaussians, okay? The EM corresponds with expectation maximization. I'll probably talk a little bit about that afterwards. It corresponds with a general framework, which looks a lot like Lloyd's algorithm. Lloyd's algorithm does not quite fit into expectation maximization, but this algorithm will. And this shows up in a lot of different scenarios with modeling. And we're going to it's kind of an alternating optimization like Lloyd's algorithm. Okay. Okay, and so I'm going to kind of write it. I'm going to kind of write a version of Lloyd's algorithm, and then we're going to kind of add in some pieces, and you'll see that it's not too much more here. So my init, I'm going to choose k points S as a subset of X, and we'll set S is going to be equal to mu1, mu2 up to mu k. Okay, so just like we had the sites before for Lloyd's algorithm, we're going to have the centers of the Gaussian distribution, the mean of the Gaussian distribution. They're going to play the same role here. Okay. Okay, and I need to somehow initialize the weights too. Remember, I'm going to maintain not just an assignment of the points, but I'm going to maintain a weighted assignment. Okay, and so we're going to do for all x in x, right? I'm going to set wi, or I of x equals to 1 for phi of s of x equals to mu I, and 0 and weight of I of x equals 0 for other values of I. right? So I'm gonna start with the hard assignment, right? So I'm assigning to the closest site, just as I did before, okay. Good, so this is the initialization, basically the same as Lloyd's algorithm, right? You know, how I initialize the first K points, well, you know, use your favorite heuristic here. Again, okay. In fact, you can run any version of Lloyd's algorithm for K-means clustering to initialize if you want to. Okay, now I'm going to repeat some steps, okay? And I'm going to, so I'm gonna have 1A, 1B, 1C. Actually, let's write it up for all. This will kind of be our old 1A before, for all K in, right? So I'm going to update all the individual clusters, and this is going to have 3 steps to it. We'll call this step, again, we'll call these, what should I call these? Uppercase A, B, and C. Okay, and the first step is going to be, I'm going to set mu I as equal to basically 1 over the sum of all the x and x of x, right? So I'm going to take some sort of average here. Right? I'm going to take some sort of average of the points. Okay, but now this average is going to depend on the weight of the points. Okay, and I need to compute some total weight. So the first step is going to be the total weight here, which is going to be the sum over all the data points x times, okay, so this is going to be the total weight of cluster I, right? So the total weight of all the points assigned to it, and this is what I'm dividing by. This should be I by I. Okay, so now I'm doing a weighted average, right? Instead of giving every point a weight of 1 and dividing by the number of them, I'm weighting a point by its weight and dividing by the sum of all the weights. Okay, this is an average, but some points get weighted more. If they're more likely to be in a cluster, if they have a weight of 1, then those points get weighted more than a weight of 1/2, because I'm not as sure that it's actually in the cluster. Okay? And then there's step C here. Okay, step C for this cluster, I need to, right, so this is kind of set the mean, and this is just a weighted average. I need to do something to set the covariance here, right? And so now I need to calculate this guy, right? And it turns out that this is going to be very, very similar. 1 over, it's going to be a weighted average over all of the data points weighted by their weight. Okay, so this is a weighted average of some quantity, and this quantity is just going to be x minus mu I transpose goes in the other one, x minus mu I transpose. This is an outer product. Right, so this is kind of like PCA. I've removed the center, right, of all of the data points, right? So this is kind of centering, right? I've removed the center of the data points as I'm processing them. And then I just do x times x transpose, right? If you remember that sigma I is equal to x transpose, but this is after I did the centering. Right, so it's actually x tilde, right? Because I did the centering here, because this is allowing me to do so centering, and I'm just, instead of just taking the average So each of these gives me a D by D matrix, and the entire one is just the weighted average of those D by D matrices, the covariance. Okay, and so this gives me the whole covariance matrix. I don't need to take the eigen decomposition of this. I can just store it like this. This is all I will need to evaluate the Gaussian. Okay. Yep.
So if we're making these sums, are we doing it for every x in the whole set or every x in the cluster?
There are no points in every point is in the cluster. Just some of the weights might be 0, right? So if it's definitely not in the cluster, the weight will be 0. It turns out in this formulation, all the weights will be greater than 1.
If we have one classified.
There's no classification. All the weights, now some weights might be really close to 0 and some really close to 1, and that will tell me, okay, I'm pretty confident in this cluster, not the other one. But there, as we'll see, we'll calculate next. And when they start out, there are 0 or 1, right? But as we'll see next, they're going to be somewhere between 0 and 1. They're never going to be exactly 0 or 1. Yeah.
So for 1A, when it says like we're okay, 1A, that's supposed to be I.
Oh, yes.
Yeah.
Yes. Thank you. Thank you. Yeah. So this is for all clusters. We're going to update. This is finding the optimal kind of model for the clusters given the weighted assignments. All right. Okay. Let's complete this. There's one more step. I need to then 1B. I need to for all x in x. Now I need to update the weights. Right. This is to update model for each cluster I, and this is going to be update the weight here. Okay, now to update the weight, okay, what I'm going to do is I'm going to say, let's do this in 2 steps. Let's say weight prime of I of x. Okay, this is, actually, let's call it L. Li of x, this is the likelihood. This is just going to be mu of I, sigma of I of x. So I'm going to compute the likelihood that it's in this model for all I, again, in 1 to k, right? So I'm going to compute the likelihood for all the model, and then I'm going to set the weight of x is going to be the likelihood of x divided by the sum of, running out of space here, over the sum of I equals 1 to k of the likelihoods of x. Okay, so I'm normalizing, so this is in 0 and 1, right? So this quantity is between 0 and 1, and this quantity is between 0 and infinity. Okay, all these values, because we're using a Gaussian, which has infinite support, it's never going to give return a value 0. These values are all greater than 0, right? So that means that when I average this, well, there's always going to be some term in the denominator for each of the weights that is not from the most likely. So that means it's not going to be exactly 1. So it's going to be between 0 and 1 for all the weights. And this is how I update the weights. Okay, great. Some questions in the chat here. Okay, all right, so for C, okay, for C, we are multiplying the last 2 terms by the sum of the weights or those 2 terms included in the sum. Yeah, so these, yeah, so I missed some points here. Okay, so this, for C, right, the sum is over this quantity. The first one is a scalar. And then this quantity here is a D by D matrix, right? So this is a D by D matrix, and there are going to be weights in front of it. And so I'm going to add up these weighted D by D matrices and then normalize by a scalar. This is also a scalar. Okay, so it's going to output, the output of this is going to be a D by D matrix. Okay, hopefully answers that question. Yeah, so they're all defined by the sum. Yeah. Yeah, with Bayes' theorem. Yeah, we're kind of, we are indeed estimating the maximum likelihood estimator here. We are not doing, we're not enforcing a prior, so we're not like using the full Bayes rule. We're not doing a maximum a priori estimator because we're not necessarily using a prior here, but this is actually how you find the maximum. At least this is, you know, we're going to find kind of for one cluster, we're going to fit the Gaussian, which is the maximum likelihood estimator from this family of all Gaussians given this data, again, based on its weights. And that's what step 1A is doing here, is finding the most likely model given this data. And it's weighting the data points based on how sure we are they are part of this model. Okay, any other questions? I mean, there's basically you run this until it doesn't change very much or some number of steps, but this is the whole algorithm, right? So it's kind of a mess, right? It's written more clearly in the notes. So if maybe, you know, if you're not sure about some notation when you go back and look in the notes instead, it's a lot to try and write up here. But kind of conceptually, it's got the same two steps. It's the first 1A is finding kind of the optimal choice of the site for each of the clusters once you have the assignment. And then step 1B is redoing the assignment of which point goes with which site in which cluster. Except there are two changes. There are only really two changes here. There's some more notation we need to use in order to kind of express it all, but the only two changes are we are doing weighted assignments, so it's a soft clustering instead. And the weighted assignments are coming by based on the likelihoods of the model. So we say, we look at all the likelihoods, and the ones that are higher, well, those get a higher weight. And these are exponentially decaying models. So as you get far away from a model, you're very unlikely to be fit by that. So under that model. Okay, so it's going to look pretty close to a hard assignment in most cases, but it's going to be, the values are not going to be all the way zero. And the second change we're doing is we're not, okay, then we have to factor those weights into the mean. That turns out, hopefully conceptually, you're taking a weighted average instead of a uniformly weighted average. So this should be hopefully not too hard. And then step C, we're computing the covariance as well. So we're not just estimating the mean, we're also estimating this covariance, which allows our models to be non-spherical. Okay, but otherwise it looks a lot like Lloyd's algorithm, right? It's the basic thing here. If we started with this one at the beginning of the clustering section, probably would not have gotten it, but hopefully now it seems, you know, kind of like a pretty logical extension of a bunch of stuff we've done already. Yeah.
So just like with the Lloyd's algorithm, most of the time you get to a point where it's just like nothing changes. For this one, do you ever have like a slight change? Do you ever get to a point where it doesn't change at all, or is it always slight?
Yeah, it will probably always be slightly changing here, right? It's not a combinatorial algorithm, right? You're probably, if you are taking a bunch of CS classes, probably almost everything you do are these combinatorial algorithms that change its storing, pointers and assignments. And this one is not combinatorial, it's more like gradient descent. Whereas the Lloyd's algorithm was actually combinatorial, even though it was iterative. Yeah, so that one we could say it will terminate after some finite number of steps. That number of steps might be some really big exponential, but it will terminate. This one, it's like gradient descent. You're going to get closer and closer to a solution, and eventually the change will be small enough that you can stop. Yep.
Does this allow you to have more tools to better stuff case?
Yeah, mostly K is given as input here. Even there are some tools where you can say, right, like again, if you look at the total objective function here, right, you like to maximize this function, which is the total likelihood. You could say, well, let's rerun it with multiple Ks and see how much the likelihood is. The overall likelihood we found is higher than it was before, right? You can take a negative log likelihood, right? And then it becomes, you want to have a quantity which you want smaller because it's the negative in addition to the log. And that will look a lot like the k-means formulation. So this one you want to be larger, but again, the more models you fit, the more clusters you have, the larger this quantity will be, and the smaller the negative log likelihood of it is going to be. There are some criteria you could say. Now I'm specifically assuming the data is coming from these Gaussian distributions, and you can try and say, well, I can put one common thing to do is to put another term on here that says that kind of penalizes me for having more for having more clusters, saying the model becomes more complex, and there's a total amount of information I've represented here, and then I minimize the sum of those two quantities, but you need to come up with some way to balance that. And there are methods that work in this way. They try and say, how much information am I capturing, and did I really gain a lot by adding this extra term? And there's probably dozens of papers that have kind of looked at versions of this. So we do have more tools because we are now explicitly assuming a model like this. Frankly, those tools essentially come down to the elbow technique, except they're putting kind of some scoring function and some threshold on it at some point. They're saying, how much am I decreasing the slope versus plateauing? And at some point I get a trade-off, and it's kind of quantifying that technique. But they made some modeling choice in how they did that, and so it can kind of automate it. And there's more statistical modeling background here. So I feel more comfortable doing this thing than k-means, where you don't necessarily have this explicit this Gaussian assumption. It's almost there, but it wouldn't be quite right without the weights, right? And then if you're going to add the weights, well, you might as well, if you're willing to kind of do a soft clustering and add weights, well, the only difference then is the step C, and that step C is not really that hard. So you might as well do a mixture of Gaussian stuff. Unless you really think all your clusters should be spherical. If you think they should be spherical, then you should go with that. The other possible nice thing about this is this does not have an underlying assumption on the distance used. Kind of the distance we assumed that Euclidean was the right distance for k-means clustering. But it could be like the two coordinates we cared about, were heights and the weights of people, something like that. How do I compute a distance that combines together the height and the weight? Well, one way of doing that is coming up with a Mahalanobis distance instead. And this Mahalanobis distance kind of tells you, it learns how well, what a good way to combine those terms together. based on how the data is structured. So that's kind of a nice thing about this. Okay. I have 5 minutes left and good, just the right amount of time. I want to tell you about one other type of clustering, just to kind of stretch your mind a little bit about what clustering can be. Okay, and this is called mean shift clustering, and it's going to be quite simple. And so it involves a kernel, and we'll think of this kernel between two data points as typically as being some Gaussian, which is given to us. P minus Q squared divided by 2 sigma squared. Maybe this has a covariance, although that could be factored into the scaling of the data before. Okay, but this is given as input. Okay, and it's basically the algorithm has basically one step, right? It's going to be this mu of P is going to be assigning a point to so of all the data points in the set, again, the input is going to be X in RD. I'm going to do kind of a weighted average again. Okay, but now the weight is this kernel, right? So kind of if I have a point P and a point X, and there's some Gaussian, right? The weight is, the closer X is to P, the higher this weight is going to be. Okay, and so, yeah, this is the only step in the algorithm. Basically, what I do is I repeat for all P in X, I compute this, and I compute this for all P. This is 1, and then for 2, I set X equals to mu of P. Okay, and I just repeat this. Okay, so this is the whole algorithm, and this is okay. So what is going on here? Okay, let's assume this is my set X, and this, and including this set P, okay, this point P, and what I'm going to do is I'm going to I'm taking a 1 standard deviation, and this is kind of, I'm taking a weighted average of all the points in the neighborhood. Well, all the points in the neighborhood are up here, so it's kind of a weighted average, and this will be mu of P. And what happens is P kind of moves towards where most of the neighbors are. And all of the data points are doing this, right? So all the points kind of move towards where most of their neighbors are, and they tend to kind of cluster, right? And so what happens is you get kind of another set of points here, and like all these points kind of move in towards the center, and these points move in, and after a few steps, they kind of group into these, they converge to these single points, right? It happens pretty quickly, and after a few steps, they all get the same average, and all the points are at the same location, and those are kind of your centers. And the points that are all up to some rounding error at the same location, those are in the same cluster. Okay. Yeah, you'd probably use a truncated kernel, otherwise it will run infinitely and for an infinite amount of time, and it'll eventually become one cluster, but otherwise, this is the whole algorithm, and it's very different from what we talked about before, but this kind of finds clusters kind of up to some standard deviation that you've set. And it's kind of a neat thing. It's good for finding like ridges in data density and some other cool stuff, but clustering is a very vast area, and there's lots of ways of doing it, and this is kind of an example of something totally different. This one, I did not set K. I didn't set K in this algorithm. I did set some sigma. I did have to set sigma. So there's some parameter I need to set, but it was not the number of clusters. Okay, great. So we'll stop there. This is the end of clustering. We'll start classification next week. All right, and hopefully I'll post homework